Hi, and welcome to my channel, Jabber Time. Today I'm going to talk about the maximum and minimum values, the extreme value theorem. Of course, we're going to talk about the second derivative test, as you could see right here, in detail with some examples. Let's get into it. The maximum and minimum values, just by definition, to go over it a little bit quick, we have a local maximum. A function of two variables has a local maximum at AB if, of course, it's the maximum value in that area. So we say f of AB is greater than or equal to f of xy when xy is near AB. In calculus 1, we talk about interval A to B. And we say f of x is the smallest or the maximum when x varies from A to B, like within that interval. Here, when we say near, it's not fully clear, but just like in a region containing AB. We're going to talk about more details in just a few minutes. That is, f of AB is greater than or equal to f of xy for all points xy in some disk, like a circle filled including the boundary points with center AB. The number f of AB is being called the local maximum value. Similarly, we talk about the local minimum. F of AB will be the least, less than or equal, that means the smallest one in that region. So far we call it local maximum and local minimum. We're not talking about absolute. Absolute will be, of course, as we know, if you have two minimum values, two local minimum values, you compare them and you see which one is the smallest, and then you call it the absolute minimum. Now, if these inequalities hold for all points xy in the domain of f, then f has an absolute maximum or absolute minimum at that point AB. Theorem. If f has a local maximum or minimum at AB and the first order partial derivatives, which are written right here, the first derivative of f with respect to x, the first derivative of f with respect to y, if they do exist, then we have them equal to 0. Of course, like just in calculus 1, if they don't exist, it will be like a corner point. But here they're saying, like, if the derivatives are valid, they are available for us, they're going to be 0, like horizontal tangents right there. Critical points. A point AB is called a critical point of f if the first derivative with respect to x equals 0 and also the first derivative with respect to y equals 0, of course, or if one of them or both do not exist, like corner points. If f has a local maximum or minimum, then AB is called a critical point. Now, it's not the other way around. If you have a critical point, doesn't mean like you have a max or min. For example, we know that a famous example is y equals x cubed in 2 dimension. It goes up, goes through the origin and goes up again. The first derivative to test for the critical points to see if there is something going on as max and min will give you x equals 0 at the origin. But at the origin, it's neither max nor min. It's a critical point, but it's not max or min. So if we have a local max or local min at some points, we call them critical points. But if they're critical points, we have to test them to see if they're max or min. Here's an example. Now, like if you ignore everything else here, you look at x to the second in 2 dimension, and if you ignore this and call it y, just for example, that's a parabola that opens up. This is another parabola that opens up in the y point of view. So, but we are in 3 dimensions, so it's like a parabola, but in 3 dimensions. It's called paraboloid. Now, both leading coefficients are positive, so it opens up. But with these involved, that means it shifts. So it's not centered at the origin, so the vertex is not the origin. And by having this, that means we are also shifting it up. I'm going to show you the graph at the end of the example, but in the meantime, just to give you some clues about what's going on. We first find the first derivatives, the partial derivatives with respect to x and with respect to y. It's kind of lengthy to say it, so I'm going to just be referring to them as fx and fy. The derivative of this with respect to x will be 2x from here. That's a 0, that's a minus 2, that's a 0, that's a 0. And that's why I have 2x minus 2. The fy, same style, you get 2y minus 6. We set the first partial derivatives equal to 0. Make this equal 0, make this equal 0, solve for y, solve for x, and this is what I have. What does that mean? That means 1, 3 is a critical point. Is it a max? Is it a min? We don't know yet. Now we're using algebra and concepts to verify or support. So this problem is designed for understanding critical points, local minimum, local maximum, absolute minimum, absolute maximum. We're not using the second derivative test yet. In coming examples, you'll see them. So with some skills, we're completing the square. You know how to do that. You group the x's together, you group the y's together. And I'm highlighting everything or using different colors to help you understand everything right here, instead of me reading every single number. Of course, when you add 1 and 9 here, you have to balance it back to keep the equal sign. Now if you notice here, I could see the vertex, which is at 1, 3, leveled up to 4, because we are in 3 dimension. Since this is positive or 0, this is positive or 0, they can't be negative, of course. The lowest will be like if this is 0 and this is 0, so your f of xy, which is z value, will be 4. But if there's anything here or anything here, like, you know, gives you like even small amount of numbers, you're going to be greater than 4. So what does that say about the behavior of the values of f of xy or the z values? So f of xy is greater than or equal to 4. It will be equal to 4 if this is 0 and this is 0. Therefore, 4 is my local minimum. That's the concept of local minimum and local maximum. This right here, 1, 3, which makes this 0 and will make this 0, I will be with 4. That's the lowest that I could have for f of xy, because anything else will give me more than 4. So f of 1, 3 will be less than or equal to f of xy in the whole domain. So it's called a local minimum. In fact, it's the absolute minimum, because it's the only minimum that I have. If I have 2 minimums, I could compare them, but I only have 1 minimum, so that should do it. It's an absolute minimum. As you can see, we're just like supporting the concept of local minimum, local maximum, absolute, and things of that nature, with the concept that now we have 2 partial derivatives, not just 1. In calculus 1, we have dy dx, or f prime, we just call it in short. Here we have partial derivatives with respect to x and with respect to y. So this can be confirmed geometrically from the graph of f, which is the elliptic paraboloid with vertex 1, 3, 4 that I mentioned earlier right here. It's good to see it and understand more about what's happening and why we have a critical point. Those are confirmation of what is going on right there. And the 4 here when you plug in the critical point 1, 3, I get the 4, which is right there. The best way to see the 4 where it came from is this one, not this one. So if you plug in 1, that's this one here for x, and 3 for y, that's going to be 0, 0, and your output is 4. That's why your vertex is 1, 3, 4. And because of the leading coefficients, it goes up both ways, x, y, x direction and y direction, meaning both ways. And that's what we have. Find the extreme values of the function y squared minus x squared. Well, if you look at y squared by itself, it's a graph that opens, I don't want to say up, it opens up in the positive y direction, if you want to call it that way. And if you look at this by itself, this one right here, it goes with the x-axis, the positive x-axis, sorry, the negative x-axis, because it opens down. So there is two things involved, and we are in 3 dimension. So this is what we have. We find the first derivative, we find the the first derivative with respect to x, the first derivative with respect to y, we set them equal to 0, we do some algebra steps, and we get zeros for x and y. So the origin is the only critical point. Note that, which I mentioned earlier, if y equals 0, if this is not there, so I'm not moving with the y, I'm trying to look at it from one point of view, I have minus x squared, which is less than 0. Of course, if x does not equal to 0, I'm going to be with negative numbers because I have the negative sign outside. And if x equals 0, so if we eliminate this term, I have y squared, and it's always positive, of course, when you move away from y equals 0. Now, what happens is the following. Every disk, we're talking about disk like a circle filled, you know, we are not from A to B like calculus 1 on a number line. We are actually in space, and my domain starts from the xy plane. So we are centered at our point AB, which is 0, 0 in this case, and we have a disk that contains it. Every disk with the center 0, 0 contains points where f takes positive values, and takes negative values. So as you move, you're going to have to end up positive and negative depending on what type of values for x and y you're using. So f of xy at 0, 0 equals 0 cannot be an extreme value for f. So f has no extreme value because it's to be a max, it has to be greater than or equal all the time in that disk. But that's not the case that we are describing. So a function need not to have a maximum and minimum. You know that, like in calculus 1, you could have a critical point where the first derivative equals 0, but it's neither max or min. For example, y equals x cubed. It passed through the origin and goes back up, so it's neither max or min. The graph of f is the hyperbolic paraboloid z equals y squared minus x squared. I'm going to show you the graph in a few minutes. The graph has a horizontal tangent, which is the xy plane, that's differently z equals 0 at the origin. Has a maximum in one point of view, in the direction of the x-axis. Alright, so if you eliminate y, there is no y here. You could see that. In the direction of x-axis, your x moves, but there is no y. It's upside down, if you call it that way, because we are in 2 dimension now, between x and z, and that's going to be a local maximum. In the same way, when we eliminate the x and talk about y's only, so we're moving with the y, it is a positive. y square, which opens up like a paraboloid that opens up. So we have a minimum. So excuse me. So from one point of view we have a maximum at the same point, and from a different point of view we have a minimum. That doesn't work usually this way. So near the origin the graph has the shape of a saddle point, and so 0, 0 is called a saddle point. What do I mean by saddle point and the graphs that I was talking about? This is when you eliminate the y, so you're going with the x only. It's upside down parabola between x and z plane. This is when you eliminate the x and you go with the y, you're just going with the y. It's a parabola that opens up, and it talks about a minimum. This one talks about a maximum, this one talks about a minimum. This is when you go with the y and eliminate the x. This is when you eliminate the y and you stick with the x. So at this point you have a tangent. It's a horizontal tangent. It touches right here, it crosses, but at this point we have a tangent that we have some points above it and we have some points below it. And that's interesting, and that's why we bring the saddle point, because of this picture. Exactly, it describes why we call it a saddle point. Second derivative test. It's a little bit different than calculus 1. We use the first derivative test and we use the second derivative test for concavity and so on. But here is a second derivative test in vector calculus in 3D. Suppose that the second partial derivatives of f are continuous on a disk with center AB, and suppose that fx equals 0. The first derivative with respect equals to 0. The first derivative with respect to y equal to 0 also. That is, we are suspecting something here. We call AB a critical point. Now here's the formula. Capital D at that point AB is the double integral, the double differential of x times the double differential of y at the same point AB minus the derivative of x then y, or y then x. It doesn't matter at this case. There is cases, I just want to mention it. It's not it doesn't apply to this level of math at least at this moment. But sometimes students, they think like if xy and fyx is the same. Usually yes, but that's not the case. Okay, it's not our topic, so let's stick to it and keep it simple for now. fxy at AB being squared. Okay, all what I was trying to say here is don't worry about which one to do first for our section and our math assignments. But if you search online, you'll find out that there is something different about it. Now, here's the cases. If this d at that point is positive and the double derivative of f at x at that location AB is also positive, we have a local minimum. Case 2. If d is positive at AB and fxx, let me call it this way, it's faster, is negative, we have a local max at AB. If d is negative now, you don't have to go further than that. If d is negative, we have a saddle point. If d is 0, good luck, you're on your own. Gives no information. So you have to find some other way, like we described in the previous example geometrically about the paraboloid, that it's a local minimum and it's an absolute minimum, or some other ways. Or of course you could call a friend if you can, I mean. So if d equals 0, there is no information that the second derivative test gives you. So in short, to summarize that, we apply this. It takes time to do it, but it's just like algebra. skills and steps. You look at D. If it's positive, you move on. If this is positive, that's a local minimum. D is positive, you move on. If this is negative, you call it local maximum. If D is negative, it's a saddle point. If D is 0, good luck. Note, to remember the formula for D, you might say, like, how can I remember this? Well, here's one way. fxx, fyy, fxy, fyx, fyy. You just do the determinant and that's gonna end up with it. It's just like a quick hint in case. But I don't think it's hard to memorize this. As you can see, like, I'm using colors to help visualize the pattern and how it goes. Find the local maximum and minimum values and saddle points of a function of this type: x to the fourth plus y to the fourth minus 4xy plus 1. Let's look for the critical points. To look for the critical points, we find the first derivatives, we set them equal to 0 and so on. Here's the first derivatives with respect to x and y. There is too many 4's, as you could see. We set them equal to 0's. Let's get rid of the 4's. That's after you divide by 4 everywhere. Now this is critical. I know I'm using critical and it's a critical point. The key element right here to solve is you want to merge this together. And the best way to do it is from the first one, y equals x cubed, you solve for it and you use substitution to put it in the second one. And y to the third minus x equals 0. I brought it down here to show you the step. Now it's x cubed instead of y to the third minus x equals 0. And this is the steps. I don't want to go step by step here and take your time. It's a lengthy video compared to my other videos. So I'll just go over it quick. This is x cubed minus x. Factor 1x out. Now this could be looked at difference between two squares, as this is 1 to the 8th, or this one now is x to the 4 to the 2nd. So I could look at them as a difference between two squares. This is also a difference between two squares, looking at it as x to the 2nd to the 2nd. As you could see, now again x to the 2nd minus 1 will give you x minus 1 times x plus 1. Simplifying this or solving using the principle of zero products, I get 3 values. I get 0 from here, I get 1 from here, negative 1 from here, and complex or imaginary numbers from here. So 0, 1, negative 1. Taking these numbers back in to find the values, it came up to be the same. So as coordinates, we have 3 critical points. You could see them. Let's use the second derivative test. Now we find the critical points, then we use the second derivative test to test each one of them. And here we go. Here's my function. Here's my first derivatives with respect to x and y. To remember the capital D, we need fxx, we need fyy. Find the derivative of this with respect to x. Take a look. That's going to be 12 x to the 2nd, and this is 0, so I have it. Find the derivative of this with respect to y. Same style. Now you have fx equals 4x cubed minus 4y. Find the derivative of this with respect to y. You get what? Minus 4. It's right there. Find the derivative of this with respect to x. It gives you minus 4. You could do it either way, but as I said, just a comment that that is not true like from each one of them in some functions, which is another topic. At least for now, just keep it this way and be aware. So here's capital D. Just follow the steps, plug in the numbers, test is positive, negative, 0, and so on. We have like what, 4 cases. Take one point by one point. Take the values that we found, put them right here to simplify. What's capital D? Capital D is 144x squared y squared minus 16. Take the 0, 0. Test it. put 0 here, put 0 here. I have minus 16, which is negative. That's a saddle point. That's case number 3. So the origin is a saddle point. Take 1, 1. Plug 1 here, plug 1 here. Now this is positive, so I move on. The fxx, I just want to say it this way quick, is also positive. We have a local minimum at 1, 1. Negative 1, negative 1. Do the same style. I get positive for d, positive for fxx, same thing, case 1, local minimum. So, but if you notice the same values, let's see. Oh, right here. The image of f is negative 1 and the output of f is negative 1. Same level. So I can't call this one local minimum and I call this one local absolute minimum. They're both the same. So I could call them both absolute minimum. Just for your info. Now, to describe the whole thing as a graph, because visually it helps a lot to understand what's happening and why we have a saddle point here and a local minimum here at the same level like local minimum here. Here's the detailed graph. This is what I have, and this is what I was reading. I just kept them next to the graph to see it. That's my graph. Local minimum, actually absolute minimum. And this point here, if you go from one direction, it goes this way. If you go from the other direction, it goes this way. That's called a saddle point. It looks like a pants. And this point right here is actually, it's not local maximum and local minimum. You could tell. Okay, from one direction, it looks like it's a minimum. From a different direction, going this way, it looks like it's a maximum. So that's called a saddle point. Find the shortest distance from 1, 0, negative 2 to the plane x plus 2y plus z equals 4. Now, we know that we have similar examples in calculus 1, but this is interesting because it's in a 3D. If you notice, I had the z in green because I wanted to focus with me as I go on this part right here. Now, to visualize, you don't have to, but to help understand, build the equation, because, or solve a problem, we need to know what's going on. So I think a short graph will help. We have a point that is fixed. That's 1, 0, negative 2. Now we have a plane here. I don't have to graph the plane from the plane, you see? The plane has a point that is a mover. It moves on it. So in general, it's called XYZ. Notice again, the Z is in green. We know the distance formula, which is actually Pythagoras theorem, between 2 points in the XY plane. We're going to apply it to the 3-dimension, and that's how it looks like. The distance between the fixed point and the point that moves. So it's going to be x minus 1 to the second, y minus 0 to the second, z minus negative 2 to the second. Under the square root, I'm going to call it little d because to distinguish between the second derivative test, it's called capital D. Simplify this. I don't need to keep the 0. I don't need to keep the minus negative sign. And now, we need to minimize this. The shortest distance means minimize. Well, to minimize this, you could just minimize it without square root. I'll show you just in a second. Now, this is still green. That's 1, 2, 3 variables. That's a lot. By taking this z from here and write it as a function of x and y and substitute it here, my whole thing becomes a function of x and y. You always want to think this way. When you use second derivative test, you want to minimize a function, you want to maximize a function that you have, you need to reduce your variables from 3 to 2. And here we go. We're going to take this and substitute. Now notice that I squared both sides because I don't need the square root in my way. So that's going to be called d squared. Now in blue I wrote it as f of x and y. If I minimize this, that means d squared, that will be the minimum that I get out of d, the distance. So our focus now algebraically or mathematically is to work on this new function. This is my new f of xy. So that's my function. It's in terms of x and y. We find the derivatives with respect to x. We find the derivative with respect to x and set it equal to 0. Simplify this. Trying to save you some time from reading every single number. With simple algebra, you could find the values that leads to f of x equals 0 and f of y equals 0. I have them for y and x. And doing some algebra, you get one critical point. And we're supposed to have one critical point because of the concept that we have, 11 over 6 and 5 over 3. Now, second derivative test. This is our function. As you know, these are the first derivatives. I don't want to put this on the same slide before because that's going to make everything compact and so small. So I don't like that. I like to keep everything that relates to the problem on one slide at the end of the presentation, but sometimes I'm forced. That's why I'm carrying some information to the new slide to show you and keep you with the details. Once you have the first derivatives with respect to x and y, you know how to do this. You could test it. Just follow the formula. Now notice right here that d is 24, which is positive. You know, in the first case and the second case of the first derivative, the second derivative test, once you find d that is positive, you go after fxx and see if it's positive, you call it local minimum. If it's negative, you call it local maximum, and so on. If it's negative, that's case 3, and if it's 0, that's case 4. So now I need to go over and test this, but it's already there. Look, it's positive. So what do we have? We have fxx is positive, and we have d is positive. If you notice here, I'm trying to write less, but if you plug in the numbers, you get, let's see, we have, these numbers right here, they don't need even to plug in the points, as you can see. I don't have to. I only have one critical point, and this is what's happening. So f has a local minimum at 11 over 6, which is case 1 in the second derivative test. I have 4 cases. At the critical point that we just mentioned. It is actually the absolute minimum. Why is that? Because there must be a point on the given plane that is the closest to this point 1, 0, negative 2. If you take that d that earlier we have, which is square root, which is a distance, not fxy, and plug in the numbers that we have for x and y from the critical point, I get 5 square root of 6 over 6. So the shortest distance from 1, 0, negative 2 to the plane that was mentioned to us as x plus 2y plus z equals 4 is 5 square root of 6 over 6. And that should do it. A rectangular box without a lid is to be made from 12 meters square of cardboard. Find the maximum volume of such a box. You've seen similar ones in Calculus 1, and here we go. Those are good practice problems. Here's the box. Let's give it the dimensions x, y, z, as you could see. So what's the volume? The volume is going to be x, y, z. Notice I'm using green for z. One more time. just like the previous example. The area of the four sides that I'm using to build the box is out of the cardboard that I have. So I have one base, which is xy, and I have this side identical to that. So I'm gonna find this, which is x times z, double it, times 2, and that side in the back and this side in the front, if you call it that way, I'm gonna double it. So these are doubled, and that's the base. 12 is what I have here. Let's solve and make z by itself, z as a function of x and y. And I think you know the rest. You know where I'm taking you, right? Just like the previous example, you need those skills to start, because if you can't merge things together and have a clean function to start finding derivatives with respect to x and respect to y, it's a little bit hard. So you need to know how to start. That's my hint to you. So, but v equals xyz and z equals so and so. I'll just take that z value and substitute that right here, as you could see. Simplify this, make it one fraction. Find the derivative of v, which is usually it's called f, but let's keep it this way as v in this case. My function v is a function of x and y. We're gonna find the partial derivatives of v with respect to x and with respect to y and apply the second derivative test. With skills that we know about the quotient rule, this is dv dx and this is dv dy. Notice that I'm highlighting a few things for you. Here I have y squared, here I have x squared, and this is square and this is square. So those won't contribute anything about natives. They'll just say positive all the time. And what's inside here, it's almost identical to what's inside here. But the difference is x squared here and y squared. If v is a maximum, then dv dx, dv dy equals 0. We're looking at critical points, right? But if y is 0 here, or x is 0 here, the whole thing is going to be 0. You go back right here, that will make the derivative 0, of course, critical points. But that doesn't make sense in the problem, because if x is 0, I'm having a box that doesn't have any length. And I'm looking for the maximum volume, so that should be rejected. So we must solve for the equations. I'm not worried about x to be 0 or y to be 0. I'm looking at this to give me zeros. Alright? Now, if you solve by elimination, these are identical. As you can see, I kept them in red for you to see it clearly. They're going to cancel. And I'm carrying them to a new slide, as you can see. They're going to cancel, and this is what you're going to have. So if x squared equals y squared, and of course we're not using x to be negative length and y not to be negative length, so I'm not going to use a plus minus. It just says x equals y. I don't want to say x equals minus y and so on, because you know we're dealing with the box and x and y, they're not supposed to be negatives. If we put x equals y in either equation, either one of them, we get 12 minus 3x squared equals 0. Simplifying, solving for x, I get x equals 2. Let's give it a test. 2 squared is 4. 3 times 4 is 12. 12 minus 12 is 0. If x is 2, but we're saying y equals x, so y is 2, Go back to the z from the previous page, which was a fraction in terms of x and y. It gave me 1. So we have 2, 2, 1. We could use the second derivative test to show that this gives a local maximum of v. Or we could simply argue from the physical nature of this problem that there must be an absolute maximum volume. Of course, if we go the other way around, it's going to be an absolute minimum where there is no box volume of 0. Must be an absolute maximum volume which has to occur at the critical point of v, so it must occur when x equals 2, y equals 2, and z equals 1. Then v equals 2 times 2 times 1 equals 4, so the maximum volume is 4 meters cubed. Absolute maximum and minimum values. How do you get the absolute maximum and minimum values? Well, I'm gonna take you step by step instead of wasting your time talking about, critical points, endpoints, and so on. Let's just do it step by step. The extreme value theorem, EVT, in one dimension, in calculus 1, for a function f of one variable, the extreme value theorem says that if f is continuous on a closed interval, so you do have the endpoints to use a to b but closed, then f has an absolute minimum value and an absolute maximum value. It guarantees that. According to the closed interval method, we find these by evaluating f not only at the critical points inside the interval or within, but also at the endpoints a and b. That was two-dimension calculus 1. Now, let's talk about vector calculus. The extreme value theorem in 2 dimensions, this is called closed. I'm not looking at an interval like calculus 1. This is a closed region that we have. I don't want to call it interval. This is closed. Well, if you have this, a disk that is including the inside points and the points on the circumference, that is called closed. If you're missing a point right here, like this one, that's not going to be closed. Just by missing one point, that makes it not closed. Of course, it does make sense. This one is not including the boundary. That's not closed. This one is not including the boundary from 3 sides. That's not closed. So that's a visual look what's closed and what's not closed. Just to apply the extreme value theorem concept from calculus 1. A closed set in r to the second is one that contains all its boundary points. For example, the disk D equals x, y such that x squared plus y squared is less than or equal to 1. Less than or equal to 1, that means you are n and you are equal. So you are containing the boundary points and the inside part. That is like 2 statements in one. I'm referring to this because it looks like our case, a circle centered at the origin with a radius of 1, including the inside parts. That's why it's called disk, which consists of all points on and inside the circle x squared plus y squared equals 1. Is a closed set because it contains all of the boundary points, which are the points on the circle x squared plus y squared equals 1, and of course the inside part. But if even one point like this right here on the boundary curve were omitted, the set would not be closed. Now let's apply the extreme value theorem for functions of 2 variables. If f is continuous on a closed bounded set D in r to the second, then f attains an absolute maximum and an absolute minimum at some points, x1, y1, x2, y2, as you could see. To find the absolute maximum and the absolute minimum values of a continuous function f on a closed bounded set D, step 1. Find the values of f at the critical points in D, inside. Step 2. Find the extreme values of f on the boundary of D. Step 3. The largest of the values from step 1 and step 2, when you compare them, is the absolute maximum values, and the smallest of these values is the absolute minimum value. Here's an example about the extreme value theorem to explain all these 3 steps and how do you apply it with the boundary points. Find the absolute maximum and minimum values of the function. I have a function right here. This will be my surface in 3D. But my domain is down below. This is the domain. X and Y, it's a rectangle. So the surface is above the plane right here. That is a curve. It goes up and down, as you could see. X squared minus 2xy plus 2y is not a plane. It's a surface. So above this point it could be higher. Down here it could be lower. It goes back up and things of that nature. My domain is being described right here, where x is greater than or equal to 0, less than or equal to 3. From 0 to 3 including both. Y from 0 to 2 including 0 and 2. So it's this rectangle including the boundary, so it is closed. Since f is a polynomial, it is continuous on the closed bounded rectangle D. So by the EVT, there is both an absolute maximum and absolute minimum. It guarantees that. Let's find the critical points. You know how to do it. We take the function. We find the first derivatives with respect to x and respect to y, and we set them equal to 0. That's my first derivatives. We set them equal to zeros. So we have the critical points, solving for x, solving for y, 1, 1. And when you plug 1, 1 in our main function, you get also 1. But where is 1, 1? If this is 0 and this is 3, so 1 is somewhere here. And if this is 0 and this is 2, 1 is somewhere in the middle. So somewhere here, it's 1, 1. At this point, 1, 1 in the domain, the graph has an output or a level at 1 also. And that's a critical point. Now we don't know if it's a minimum at that location or it's a maximum, local minimum or local maximum. We're going to find the extreme values of f on the boundary of D. Now, in 2-dimension calculus 1, we just like have a and b. We just plug in a, we plug in b, and that's how we finish the extreme values on the boundary points or end points. At that time, we used to call them end points, and we compare. But in this case, we're gonna just break it down and handle it this way, which consists of the 4 line segments L1, L2, L3, L4, L1, L2, L3, L4. So we're going to break it down to 4 pieces. We're going to go over L1. On L1, notice that y is 0. Notice that also that x changes from 0 to 3, including 0, including 3, which I have it written here for you. So if you go back to the equation and you force y to be 0 because you're walking here, Actually, you're not walking here. That's your domain, and you're up on the surface. So if y is 0, this will cancel, this will cancel. And what you have is x squared only, by forcing y to be 0. But that is a behavior of a parabola values. And you're going from 0 to 3, so that keeps increasing as you plug in 0, 0.1, 0.2, 1, 1.2, 2.5, up to 3. It increases. This is an increasing function of x. So the minimum occurs when you start, which is f of 0, 0, which is 0. And the max will end up at the end. So I don't have to stop in between to look for some extreme values, if you know what I'm talking about. Because the graph, or the values, not the graph, they go like this. So it keeps increasing when you trace it on the surface S. So all what I need is the endpoints and find the values. Let's go to L2. On L2, x is fixed to be 3 and y changes from 0 to 2, which I have it written for you. Go back to the function, force x to be 3, force x to be 3, simplify, and that's what we have. Now if you go from 0 to 2 as your inputs right there, you have a negative slope, so your function is decreasing, or the values, this function, specific function, tracing this points, you are decreasing. So I just need to compare the endpoints and that should do it. Here I have 9, which is agrees from the previous part when we were on L1, and at 3, 2 we have a value of 1. Let's go to L3. On L3 we have y equals 2 fixed, and we have x between 0 and 3, including 0 and including 3. Here's my function. We're gonna force y to be 2 and simplify. Well, this is a parabola. Between 0 and 3, it's not increasing all the way, and it's not decreasing all the way. This is a parabola that kind of like goes like this. So we have to look also for the vertex. Having it in vertex form, by completing the square, if you want to call it that way, I have x minus 2 to the second, which means right there at 2, the values right there, they will slow down because it opens up, as you could see, slow down, then it goes back up. I don't want to graph it this way, but we are down. This is my domain. So this is a vertex, the lowest point in values as you trace the parabola. So the minimum value of this function is f at 2, 2 equals 0, just by plugging the numbers in the original function. We're almost done. Let's go over L4. The maximum value will be 4 because I have 4 here, and I have 0 here, and I have 1 here, so the maximum will be 4. Here's L4. On L4, right there, we have the function, and we have x equals 0. So let's force x equals 0. That will cancel. This will cancel. We stay with 2y, and your y values changes from 0 to 2. This is an increasing function, and I just need to worry about the endpoints. Plug in 0, 0, plug in 0, 2, which already known from the previous pages. Now we come to the last part. Let's keep this graph and simplify or talk about what's happening. This critical point was inside at 1, 1, and the output was 1. On the extreme value, on the boundary points, we have this point, we have this point, we have this point, we have this point, and we have this point. Finding the outputs, I have 4 here, 0 here, 1 here, 9 here, 1 here, and 0 here. These are the smallest, so we have an absolute minimum at 2, 2, and at 0, 0. This is the absolute max, value, which is 9, and it occurs at 3, 0. And this is what I have right here for you. Of course, comparing it to this one. Those are lower than 1, and this is higher than everybody else. So we take the critical points, we test the boundary lines, and we move on from there. The absolute maximum value of f on D is f of 3, 0, which is 9, and the absolute minimum value of f on D is f of 0, 0, which is f of 2, 2, and the value is 0. It's a lengthy video. It's about 54 minutes or so. Hopefully you like it, and if you do like it, I do really appreciate if you stayed with me till the end of this video. It's a lot of information, and I don't feel like it's worth to drop most of the information and make it like a 25 minutes video. Thank you for being with me, and I'll see you in the next one. Thank you. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.